Hello all. So in this project we are trying to use the DMA based data transfer to our peripheral. So as I mentioned before, we are going to use Xilinx IP core as the DMA controller, but one thing that we are missing is a peripheral, okay, to which I will transfer data. So we'll make a simple peripheral. Now remember, the interface between the DMA controller and the peripheral is AXI4-Stream based. So let me give a quick overview of the AXI-Stream interface. So again, as I mentioned before, AXI-Stream, it's a point-to-point interface. The bus is not shared. There is a dedicated bus between a master and a slave. And there are very few mandatory signals on this bus. So as you can see in this picture, of course, this is a synchronous interface. So there is a clock going to both master and slave. Then we have the data bus, which can be 8-bit, 16, 32, any width that you wish. Then there is a valid signal going from master to slave. This signal basically indicates the data on the data bus is a valid data. So only if valid signal is high, it indicates the data is valid. Otherwise, whatever data is on the data bus is an invalid data. Similarly, there is a signal called ready coming from the slave to the master, which basically indicates the slave is ready to accept a data. Okay, now let's look at the waveform during data transfer. Okay, so here you can see clock is running. This is the valid signal. This is the ready. This is the data. Now on this clock, the master is saying he has a valid data and he places 15 as the data. And the ready signal is already high from the slave. And on the next clock, if you see, the valid as well as ready, both signals are high, and that constitutes a valid data transmission. So in AXI4-Stream interface, a valid data transmission happens only when both valid and ready signals are high at a positive clock edge. Okay, usually positive clock edge, can be negative also, but generally we work on the positive clock edge. So on this clock edge, both valid and ready are high, and the data is actually 15. So this 15 gets transferred from the master to slave. Similarly, on this clock edge, again, valid is high, ready is actually high. Only after this clock edge, ready is going low. So this 20 also get transferred. Now, if you look at this clock, okay, so the master is saying he has a valid data. The data is 45, but the ready signal is low. That means the slave is not ready to accept data. So in this case, there is no data transmission happening. Now, if a valid data transmission doesn't occur, the master should hold the data on the bus until the slave is ready to accept it. So after this clock edge, okay, after this clock edge, ready becomes high. So on this clock edge, ready is high, valid is high, and the data transmission happens. And after this clock edge, valid goes low, indicates the master he no longer has a valid data. So although the ready is high, on the next clock edge, no data transmission happens because there is no valid data. Okay, so this is how AXI4-Stream works. The only thing to remember is data transmission happens only when valid is high as well as ready is high. Now you will notice that there is no concept of address here because it's a point-to-point. Okay, so there are dedicated bus between master and slave. So there is no concept of address here. It's a point-to-point bus. So that's it. Now we prefer AXI-Stream because it gives very high performance. If you look closely, AXI-Stream can provide one data transmission per clock cycle in ideal scenario. Okay, so if master always have valid data and if the slave is already always ready to accept data, you can have one data transmitted every clock edge. But if you look at AXI Lite interface or even AXI4 interface, this is not possible because it's a address data interface. So first the master has to send the address, the slave need to receive the address, then he has to send the data, then he has to accept the data, so on and so forth. So it will take several clock cycles for even a single data transmission in AXI Lite interface. AXI4 full is better than AXI Lite because there's the concept of bursting. That means the master sends the address only once, and after that he sends a burst of data. So there also data transmission can happen on every clock edge to certain extent. Like you usually have a burst of 16 or 32. So after that, the master again has to send the address. So there will be a break in data transfer. So AXI-Stream gives the highest throughput actually. But the drawback is, again, this is not memory mapped. So a peripheral which follows AXI4-Stream interface cannot be directly interfaced with the Zinc processor part, PS part, because PS has only AXI4 interface. Whether it is GP port or HP port, they support only AXI4 interface. They don't support AXI4-Stream interface. So you cannot directly connect them. You can connect the stream interface only through some kind of bridge actually. So in our particular case, this bridge will be the DMA controller, which supports AXI4 interface. Okay, fine. So I guess you understood about the protocol AXI4. So the first thing we need to build is a peripheral which we can use for testing the DMA transfer. Okay, so AXI4-Stream peripheral, you can build it in different ways. One is the same way you build a AXI Lite IP, same style. You start a project and go to tools and say you want to create a new IP and choose the IP. And when you choose the IP interface, you choose AXI4-Stream instead of AXI Lite, the way we did last week. Last time we chose AXI4 Lite. Instead of that, you just choose AXI4-Stream. That is one way of doing it. But the template generated by Vivado for AXI-Stream is a little bit complicated. So there are much more signals than the valid, ready, and data. There are other signals also in AXI-Stream, but none of them are mandatory. They are all optional signals. Okay, only these three are the mandatory signals. So the template from Xilinx, they have these optional signals also, so things may look a little bit more complex. So instead of that, what I will do is I will directly write my Verilog code for a AXI4-Stream peripheral. Then from that code, I will create an IP instead of starting from a IP template and editing it. Okay, so that's the approach I'm going to do now. So I'm going to project, I'm starting a new project, and the IP I'm going to call it an inverter. So it's a very simple IP. What it does is whenever it gets the data, so from it can be 32-bit wide data. Okay, so what it does is each byte of this 32-bit, so we have total 4 bytes in 32-bit, each byte will be subtracted from the number 255. Okay, so why we are doing it will be clear to you later, because this is a so-called inversion operation in image processing. So image processing, you have pixels. If I'm talking about grayscale image, we have image pixel values from 0 to 255. So if you subtract these pixel values from 255, you will get a negative image of the original image. Okay, so that's the effect, because white will become black and black will become white, and all the values in between will be getting inverted, because the maximum value is 255 and minimum value is 0. So you'll feel like you are having a negative image. Okay, so that's the IP I'm going to build. So I'm going to call it inverter. Now I am directly choosing my IP repo to store this IP, because as I said before, I am directly starting to code for this IP. So I am choosing my IP repo directly, so that all the source code will directly get stored in that folder. Okay, so previously only that edit IP project we used to keep it in the IP repo. In this particular case, I won't have that edit IP project. I am directly writing my code in this project itself, so keep it directly in the IP repo. Otherwise, everything else is same. Okay, so I am directly writing my code. So I am calling it inverter.v. Now, as I mentioned before, what happens is the inverter gets some data and he takes byte by byte from that and subtracts it from 255 and sends it out. So he needs an interface which accepts data. He needs an interface which sends out data. Both follows AXI4-Stream interface. Now the interface which is accepting the data, that is a slave interface. So we need a AXI4-Stream slave interface, and the interface which sends out data, that is a AXI4-Stream master interface. Okay, so the interface which is receiving data, we call it as a slave interface. The interface which sends out data, we call it a master interface. So this IP has both a slave interface and a master interface and the common signal. So we have input clock. So let me call it AXI clock, something like that. We have reset, AXI reset. Now AXI protocol requires reset signals to be active low. Okay, so I'm directly taking it as an active low signal to indicate that I'm putting an N at the end, negative. This is active low signal. Now slave interface, we have a valid signal coming from the master, the data coming from the master, and the slave interface sending out a ready signal. Now I'm going to use the style used by Xilinx themselves. So I will call it S underscore AXI-Stream valid to indicate this is a slave interface and this is AXI-Stream protocol and this is the valid signal. And input, let me make a 32-bit data interface. You can either write 32 there or you can parameterize it, and here you can write hash, okay, parameter data width equal to 32 and use that value instead of directly giving 32 here, so that in future if you want to change the data width you can change. As axis data, now we have the output which is as axis ready. Okay, so that makes our slave interface. Now master interface, we have output m-axis valid, output data width -1 down to 0, m-axis data, and we have input m-axis ready. Okay, so that's it. Now let's write the code. So my aim is to take this data byte by byte and subtract it from 255 and give it to this bus. That's it. Okay. Now, as I mentioned before, we are working on the positive edge of the clock. Okay. I need to take this data. When I should take this data? Only this is a valid data, and I am ready to accept that data. Okay, only under that case I will process data. So we will write if s-axis valid, there is a valid data from the master, whoever is giving data, and if I am ready to accept that data, under which condition I will be ready, under which condition I won't be ready, we will see later. But for the time being, this constitutes a valid data transfer. Okay, when this is the condition, M access data I need to modify. So this is input always block, so this should be of course a register type. Now if it is directly 32-bit, like 31 down to 0, you will write something like that. You need to subtract S axis data from 255 byte by byte. So you may write 255 minus 7 down to 0 is 7 down to 0. Like that. You need to do it byte by byte. That's why we are writing like this. 0 to 7, then we have 8 to 15, we have 16 to 23, and we have 24 to 31. Same values here. Okay, so this is how we write if it is fixed 32-bit. Now if you are parameterizing it, okay, so we need to write a general case. So I will use a for loop in this case. You haven't seen for loop in synthesizable Verilog code before, so that's why we won't make a blank statement like you cannot synthesize or implement for loop or while loop in Verilog. You may or may not be able to implement a for loop depending upon the coding style and depending upon for what purpose you are using a for loop. So let me try something like this. For I, so the syntax looks exactly like our C syntax. So this I has to be declared. You can declare it as integer type actually. For I equals, so instead of writing like this, I need to write this in using a for loop. So I will find out how many times I need to divide them into multiple bytes. Okay, so I equal to 0. How many bytes I have depends upon my data width. So the data width divided by 8, right? So I will take I less than data width divided by 8. I unary operator is not supported. You cannot write I plus plus. You have to write I equal to I plus 1. Begin end. So how you'll write M axis data. So if you see here, you are going like first 0, then 8, then 16, then 24. If you relate it with I, this lower index is basically I times 8. Okay, and the upper index is 8 more than the lower index. Okay, so slightly confusing. You need to count including the starting index. So 0 to 7, there are 8 bits. So I times 8 plus colon 8. Okay, so this syntax look little bit weird, but this is how you should write. You cannot write I times 8 here and I times 8 plus 7. Okay, so it looks like this is, or I times 8 plus 7 here, and I times 8. Okay, so you wanted to write something like this, but unfortunately when you go for synthesis, this will give an error saying like your index is not a constant. So Verilog, it doesn't let you use a variable in the lower index as well as the upper index. So we have to follow a certain style of syntax. Okay, so we need to follow something like this. I times 8, you say how the lower index is found, and you need to say how big is the upper index compared to lower index here. I times 8 plus 8. Same way here, you need to say 255 minus, here I made a mistake. This is M axis, all this should be S axis. Let's correct it here. S axis, because that is your input data. This is your output data. M axis S data, and we just copy paste this. And we remove this. Now this became a generic case. So what happens is during synthesis, Vivado will unroll this loop because this will be a constant value. Based on that constant value, he will find what is the range of I. Based on that, he will unroll the loop, and this code will be unrolled, and it will look exactly same as before, provided your data width is 32, and you will have 8 lines of code if the data width is 64, so on and so forth. So Vivado will do it for you. Okay, so that's the idea. Okay, so if this is valid and this is ready, this is what is going to happen. Makes sense. Now always at for such AXI clock, you need to make this output signal next. AXI valid. So I'm going to use it inside always block. So make it reg type. Okay. When do you have a valid data as output? You have a valid data as output when you have a valid data as input and you already processed it. Okay. So since this processing is happening on clock edge, your valid data will come out 1 clock after you receive an input valid data. Okay, so this M axis valid data is basically this. Your output data is valid when you have a valid input data and you accepted it. If both things happen, you have a valid data. Now if you look at the wave diagram, this will coincide with this valid actually. So when you have an output valid, you have a output valid data. So that's also done. Now the only thing remaining is this ready signal, M axis ready signal. Okay. Now when are you ready to accept data? Now this depends upon again our hardware design. Usually when a slave becomes not ready to accept data, that usually happens if you have an internal buffer, if you have an internal memory inside your IP, and suppose your buffer is full, your memory is full, you won't be able to accept any more data from the master. So in that case, you will say like you are not ready to accept data. So in our particular case, we don't have any internal buffer. What is happening is you are getting some data from outside, immediately you are sending that data out. Okay, so you are completely in streaming mode. You are getting input data, you are immediately trying to send it out. So in that case, you won't be able to accept new data when the guy who is supposed to accept data from you is not ready. Okay, so you are trying to send out some data to some slave through your master interface, and if that slave is not ready to accept data, you will say to your master that I am not ready to accept data. So it will look something like this: assign S axis ready equal to M axis ready. If your slave is ready to accept data, you are ready to accept data. If your slave is not ready to accept data, you are not ready to accept data. That's it. So that completes our coding. If you wish, you can simulate and see. Okay, let's run a simulation quickly. Okay, let me move them back to parametric here. Data width -1. Here also data width -1. Instead of writing 31 down to 0, I have completely parameterized it. Let us relaunch since I changed the source code. Relaunch. Okay, restart. Let's give some clock frequency. Let's clock. Let's give 10 nanosecond. Okay, reset doesn't matter, but still keep it 1. Valid, let's make it 0 initially. Data, let's keep it 0 initially. Ready, don't touch. Valid data, don't touch. This ready, let's make 0 initially. Okay. Let's run at 10 nanosecond itself, so we can do clock by clock. Now suppose a master, wherever I have connected, he's giving me a valid data. So force constant 1 and data force constant in hexadecimal, let's say it's a 32-bit data. So let's say 1, 2, 3, 4, A, B, C, D. Or for simplicity, let me say FF00, FF00, FF. Okay, 1 small. 1 byte, 2 byte, 3 byte, 4 byte. Okay, and that's it. So I am running simulation. So I placed valid here, I place my data here, but the ready signal from my IP is low because the ready signal from here is low. Okay, so only when this ready becomes high, this ready will become high. That's how we wrote our code. So let me make this ready high. Force constant 1. Okay, so this ready became high, so immediately this ready became high, and on this positive edge you will see ready is high and valid is high. Ready is high and valid is high. That means this data transfer happened. Now let me make this valid signal low. Force constant 0. That means I have finished sending data. I have only one data. Now my output value became high here. You can see, and this is my output data. So I send FF00, FF00, but my output is 00, FF00, FF, which is an inverted version of this input. Okay, so my code is working. Now in simulation, when I change the signal, it is changing on the negative edge here. Okay, that's fine. If you changed it here on the positive edge, you will see your output value comes exactly 1 clock. This is the output valid. This comes exactly 1 clock after a valid data transfer. That means when both valid and ready are high. Okay, in this case, since I changed it here, he saw valid and ready on this clock cycle. That's why the output valid became high. Okay, so the code is working fine. So we can exit simulation. Okay. Okay, so our next step is to create an IP from the source code. So previously we used to go to tools and create and package new IP. So here also we'll go there. And instead of choosing create a new AXI4 peripheral, you will choose package your current project. Okay, so you are directly converting your current project into IP format. So next, and choose the option defaults here and click finish. Now this won't open a new project for editing your IP. This is what I was mentioning before. He creates this component.xml file and it opens it in the current project itself. Okay, and you can see vendor name. If you wish, you can change them, everything. Okay, so when you come to port, you will see, okay, so these are the signals that you used, S-axis and M-axis. Your clock and reset, your clock signal directly went here because based on your coding, he automatically understood this is a clock signal, so he took it there. Your reset signal he couldn't find because you didn't use the reset, so he couldn't find like this is a reset signal, so that's why it didn't go inside this option, but that's fine since we are not using it. Now, one thing, when you go for the GUI here, you can see this is how your GUI, your IP will look like when you go for the block design, and you will see like your AXI-Stream interface. Instead of showing it as a single interface, it is showing it as 3 different wires, and it has mixed the master and slave because Xilinx, they always keep the inputs on the left and the outputs on the right. Based on that, he put valid master data here, but slave ready here. This is fine, but it will be easier when you group the signals together which corresponds to the same interface. Remember your previous AXI4 Lite interface. There, if you look at the GUI, you will see like S_AXI, and all the AXI signals are grouped together under that interface. So we need to do something like that, and here you need to do it manually. So what you should do is you should go here and choose add bus interface. And this wizard comes up, and here you need to choose the interface definition, and we are going to use AXI-Stream interface. So under AXI, you will see 2 options: AXI memory mapped, which is for AXI4 interface, which has a lot of signals you can see, and the other one, AXI-Stream interface. So choose this one, give some name to your interface. So your slave has actually 2 interfaces. It has a master stream interface as well as a slave stream interface. So you need to give some name to your interface. So let me call it M-axis to indicate this is a master AXI stream interface. And now you need to go to port mapping, and here you have to map the signal name that you have used with the standard AXI interface signal names used by Xilinx. Okay, for example, we have S-axis valid here, but the name that Xilinx use is something like T valid. 1 second. Okay, better to start from here. So you need to basically map 3 signal: data, valid, and ready. So Xilinx use the term T data, but for master interface, we use the name N-axis data. So you need to click these 2 and say map ports, so that later Vivado will understand your M-axis data is same as the data for AXI-Stream. These are the standard name used by Xilinx. Okay, and you can see a lot of signals here. Except these three signals, everything else is optional. So that's why we didn't use it. So we need valid signal, and we are using M-axis valid, and ready signal, and we are using M-axis ready. That's it. Okay. So once you click OK here, you will see something called M-AXI-Stream here, and under that all the master signals are grouped together. Now you have to do the same thing for the slave interface also. So go here, choose axis RTL and give it S axis. You can give whatever name you prefer. And this is a slave interface actually. So you need to choose slave here, come here, T data maps to S data. Okay, T valid maps to S valid, and T ready maps to S ready. Okay. See, now M axis and X axis. Now if you come to GUI, you will see he has grouped your interface together. S axis, you can see under that your signals are here. M axis, under that your signals are here. Now there are a few more warnings here, and if you go to warnings messages, you can see what the warnings are. One warning is, okay, this we saw in the previous IP packaging also, and I told you I will explain you next time. He's basically saying you haven't specified which bus interfaces are controlled by this clock signal. Okay, now Vivado needs to know this information so that he can properly place and route your signal. So what you should do is you go to this AXI clock signal and go to parameter here and choose add parameter, and you type associated bus interface and click OK. Okay, so this is a predefined parameter, and here under value you need to specify which interfaces are controlled by this clock. Which clock? AXI clock. So our M axis and S axis, they are controlled by this clock, so that you need to give as valid. So M axis, now the interfaces should be separated by a colon actually. M axis and S axis, they are the one controlled by this clock signal. Okay, so your warning goes away. Actually there was one more warning which was basically saying you didn't specify the default clock frequency at which this bus is running. Again, that is optional parameter. If you wish, we can go and specify that also. This is the name of the parameter, frequency hertz, and you need to give the frequency at which this interface is going to run in hertz. So our system is running at 100 megahertz. You need to specify in hertz, so these many hertz. Okay. Now if you come under addressing and memory, it won't show anything because there is no concept of address here. This is a point-to-point interface, so that is blank. Now you come back here, review and package, and edit package settings. This option is automatically unhighlighted. Okay, your IP is directly stored in IP repo. That you should do when you start the project itself. You should say your project should be stored in this particular repository, and once that is done, we say package IP. And now if I go to the folder, IP repo, I have my inverter here. Now that component.xml, it got stored here actually inside my sources folder here. And you will notice like there is no folder for drivers and all. Okay, so if you go through this way of generating an IP, there won't be separate folder for drivers and all automatically generated. And there is no point in having drivers here because this is a point-to-point interface. It is not memory mapped. That means the processor cannot directly access your IP through software. So there is no concept of driver here at all. Okay, so once you have done this much, that's it. You can close this project and we can open a new project where we can add this IP and interface it with the system.